In the second video, we will continue section 4.4, modeling nearly exponential data, with an example that requires a little bit more work than the last one. And in the second example, we're going to be looking at life expectancy, and specifically this data comes from white males born in the given year. Here's the data. My first row contains the date, and this is going to be time since 1900. That means 10 corresponds to 1910, 20 means 1920, 40 is 1940, and so on. And this last date, 100, is actually the year 2000. In the second row, we see E, that's my name for life expectancy, and these are given in years. So in 1910, the life expectancy for a white male was 50.2 years. And in 2000, the most recent piece of data, the life expectancy for a white male was 74.8 years. But in this example, we're not going to try to model the life expectancy with an exponential function. What we're actually going to look at is this thing called d, and this is going to be the difference 80 minus the life expectancy. So I've taken each of these numbers, 50.2, and subtracted it from 80. So for 1910, the difference was 29.8. In 1920, the difference has gone down to 23.7, and then so on and so forth. So one thing that you should notice is that the decreases from decade to decade, and there's a few larger gaps, but these decreases are not constant. That means that this is not going to be a linear function. We're going to try to fit an exponential model using exponential regression to this data for the difference here. So to do our exponential regression, we're going to return to Desmos and repeat what we did in the previous example. So you'll begin by entering your data in a table, and I've already adjusted my graph so that we can see all of the data points. And then we'll type the same thing that we did last time. We'll type y1, that's the name of our second column, and then we'll use the tilde, and then a times b to the x1 power. So remember, a is the initial value, b is the base of our exponential function, and then x1 is the variable. And then once we're finished typing all of that, we can see the solutions for the parameters that the computer gives us. We see that a, the initial value, is about 34.72, and the base is about 0.98. Next, I want to use our model for d, the difference, to find the life expectancy e. So what you want to do is recall that the difference is 80 minus the life expectancy, and we need to rearrange this equation so that e is on one side and everything else is on the other. So what we'll want to do, or one way to do this, is to add e to both sides to cancel off this e here. And then you get e plus d is equal to 80. And then finish off by subtracting d from both sides to get rid of this d on the left. So in the end, you see that the life expectancy is equal to 80 minus the difference d. And once you have this written out, you can just plug in the expression that you found using exponential regression in the computer for d. So all I've done is replaced d with the exponential model that we found in Desmos, and I've rounded everything to 3 decimal places here. Finally, Let's use our model to estimate the year that life expectancy will be 77. So to answer this last question, we'll need to see where our life expectancy model is equal to 77 years. So first, type out the expression for life expectancy. That'll be 80 minus 34.725 times 0.983 to the t power. And then we'll need to graph in a horizontal line for 77 years. And now we'll have to finish off, zoom out a little bit to see this. This curve in blue represents the life expectancy, and the horizontal line in green is the 77-year line. And now to answer the question, we just have to see where the two graphs intersect. And we can see the number 142.822 is our answer. And well, this should be a year, and it's years since 1900, so this would translate to 2042.822.